All right, guys, so welcome to lesson 4.8. 4.8 is going to be about acceleration. I'm going to break this lesson up into 2 days. So just so you guys know, you're going to have homework for each one of the days, but the notes, you won't need to turn notes into me until we've finished the second day, okay? Because all the notes just kind of go together, honestly. So, of course, we're going to talk about reviewing what acceleration is. And then we'll look at what the units of acceleration are. We'll talk about what average versus instantaneous acceleration is, and we'll learn how to find those things. And then finally, we'll talk about how you can use acceleration to know whether an object is speeding up or slowing down. So let's go ahead and begin here. So what is acceleration? A lot of you guys are familiar with acceleration in terms of like vehicles moving. Acceleration means that you're speeding up. You're going faster and faster. So for instance, let's say you're at a stop sign and then you start to go. And after about 1 second, you look down at your speedometer and you notice that at that point in time, let me make a little table here. So at that point in time, which we'll say is 1 second, your velocity or speed is, let's say, maybe like 10 miles per hour. But then you wait like another 5 seconds and you look down at your speedometer again, and now you're up to 40 miles per hour. Well, how much did your velocity change over time? Well, we went from 10 to 40, 10 miles per hour to 40 miles per hour over a time period of 1 second to 3 seconds, or from 1 second to 5 seconds. Okay, so that would be 40 minus 10 is my change in velocity, and that took 5 minus 1 seconds. So I increased by 30 miles per hour over 4 seconds worth of time. Okay? And so that's what we would call acceleration. Acceleration tells you how much your velocity changes over time. Okay? Now, as you guys can see, there's actually one distance unit inside of acceleration, and there are 2 time units. Miles per hour can be written like this. Don't you guys agree? So I have one distance unit, miles, and I've got 2 time units. Now in the example I did, hours and seconds are different ways of measuring time, so we don't put it like that. But if you usually what they're going to do is they're going to have the units of time match. So in which case, you know, if I wanted to change this from being miles per hour into miles per second, let's say, that would change the number on the top, but I'd have miles per second. And so you end up with the time factor being squared because you have 2 time factors whenever you have acceleration. And so that's what acceleration is. It's the rate of change, or how fast your velocity is changing. All right? And we can kind of ignore this bullet. I was going to do something with that earlier, and I changed my mind, so you can just drop that out. So let's move on to our next slide here. So we talked earlier about the position function. Position, which is usually, we could use, oftentimes we use the letter S to represent position. S is equal to F of t. Now, what we learned in our lesson 4.7 was that you can find your average velocity by taking your position at one time and subtracting it from your position at another time and dividing it by the total time. But then we found that if we find the limit of that as the 2 times become 1, you end up with an instantaneous velocity, which is basically just the derivative of the position function. So that's all stuff that we've already learned there. Now, what about acceleration, though? Acceleration, you could find average acceleration in much the same way that I just did on the last slide. You could take your first acceleration and subtract it from your first velocity, and subtract it from your second velocity, and divide by the total time. So if you take your second velocity and subtract from it your first velocity, that'll tell you how much your velocity changes, and you divide it by the total time. And that's what I did in the last slide. We had 40 miles per hour, we had 10 miles per hour over 5 seconds minus 1 second. And that would be my average acceleration. It tells you how much the velocity changed over time. Now notice the difference. It's not f minus f like it is up here with the velocity. It's not position minus position. It's velocity minus velocity. So it's f prime minus f prime will tell you the acceleration. And once again, if you were to take the limit of acceleration as your second time approaches your first time, then that's going to basically turn this difference quotient into a derivative. And so if you take the derivative of the derivative, you get a second derivative, right? So the second derivative of your position function is acceleration. And so here's a summary of the topics then. We have two different averages. To find the average of velocity, you do position 2 minus position 1 divided by the time. To find your average acceleration, you do velocity 2 minus velocity 1 over time. To find your instantaneous values, the velocity is the first derivative of position, acceleration is the second derivative of acceleration. So this is a nice little summary of both of those things. So let's go ahead and put these things to work for us here and start off with example 1. All right, so number 1, use the velocity table below to answer the questions that follow. So I call this a velocity table because it tells you the velocity of an object at certain points in time. So for instance, at t equals 3 seconds, the velocity of some object that's moving is 15 feet per second. So this is a table that tells you the velocity of an object at specific points in time. So what they want us to do is they want us to find the average acceleration of this object on the interval from 3 to 15. Well, average acceleration is equal to velocity 2 minus velocity 1 over time 2 minus time 1. And since we're looking at the time interval of 15 to 3, those are my time values. So I'm going from 3 to 15, so that would be my time length. T2 is 15, T1 is 3. And at t equals 15, my velocity is 63. So my second velocity will be 63. And at t equals 3, my velocity is 15. So my first velocity is 15. So I'm going from a velocity of 15 feet per second, and I'm increasing that to a velocity of 63 feet per second, all over a time period of 15 minus 3 there. So let's go ahead and simplify this and see what we get. 63 minus 15 is going to be 848, I believe. Is that right? I think so. And then 15 minus 3 is 12. And then we divide it and we get 4. But we don't want to forget our units, okay? Now, these top numbers here, these were velocities, right? And velocity has units of feet per second. The denominator numbers, though, were time values, and the time values are in seconds. So it's feet per second, or in other words, feet per second squared. And that's my acceleration, my average acceleration on the time interval from t equals 3 to t equals 15. Now in our last lesson, we talked about how you can estimate the instantaneous velocity of an object by picking an average velocity that's really close to your instantaneous velocity, right? Well, you can do the same thing with acceleration. If you want to find an average acceleration, an instantaneous acceleration when you're doing a table problem, what you're going to do is you're going to find the average acceleration that is closest to the instantaneous point that you're interested in. All right, so use the table to estimate the instantaneous acceleration at t equals 2. So my instantaneous acceleration at t equals 2 would be really close to, or approximately equal to, the average acceleration for the two time values that are closest to t equals 2. So what two time values are closest to t equals 2? Well, that would be 1 and 3, right? So my instantaneous acceleration at t equals 2 is going to be approximately equal to the average acceleration that takes place on the time interval from 1 to 3. And since we know how to calculate average acceleration, we do t2 minus t1. And on the top, we have v2 minus v1. And then we go ahead and calculate it from there. We get 8 over 2, which once again is 4. And the units are going to be the same. It's still feet per second squared. And so this is my estimation of what my instantaneous acceleration would be at that point. Okay? On FRQs, I don't think they're too picky about this, but I think it would be wise to make sure that you write like I have here. You don't want to just put that the answer equals 4. You want to say that the instantaneous is approximately equal to the average, and the average equals 4. Okay? So just something to keep in mind. I don't know if they're too picky about that, but something tells me that that could be a relevant concern. Well, that being said, let's go ahead and move you guys into trying one. Before I do number 2, I want to let you guys practice this table stuff a little bit. Go ahead and pause the video here and do this number 1, and when you unpause it, you'll see the solution. Okay, here's your 2 answers. I'll let you guys study that for a minute. But once you're done studying it, you might want to pay attention to my interpretation of these things here. So what this means, you guys, is that your velocity is increasing at 9.3 liters per minute every minute. Okay? Why is it increasing? Well, it's a positive. My acceleration is positive. So that means that this velocity, or the rate of change of the liters, is increasing at a rate of 9.3 liters per minute every minute. So same thing here. In this one, the instantaneous rate of change at t equals 8 is approximately increasing at a rate of 12 liters every minute. 12 liters per minute every minute. Okay? And so there is your interpretation. Let's go ahead and backtrack now. We'll do the second problem on that slide. Going to be the same types of questions, but just coming at it from a different angle. Instead of giving you a table, I give you an actual equation. And so when you have an equation, you can actually find actual instantaneous accelerations and whatnot. So the position of an object thrown straight up into the air is given by this function that you see here. Find s prime. What does that represent? Well, that's the derivative, so that would be negative 32t plus 20. And what that represents is the velocity of the object at any given time. Part B, find s double prime. So that means find the second derivative. So that means I'm going to take the derivative of the derivative, which would just be negative 32. And that represents the instantaneous. Actually, we should be more specific up here in part A as well. This is instantaneous velocity, and this is instantaneous acceleration. Okay. Part C is asking us to find s prime of 2. Well, s prime is acceleration, right? But what's up with the 2? Well, that 2 means we're going to plug that in for the t, which means that 2 is a time value. And so when we simplify this, that tells us that our velocity at t equals 2 is negative 44. Now we can actually give it some units, I think. Did I give any units? Oh, I didn't. You will have some problems sometimes where they don't give units, so you don't need to say feet per second or anything like that. You can just leave it because they didn't give you units. I don't see any on this problem. All right, let's take a look at part D. Find S prime of 4. What does that represent? Well, it's actually just a repeat question. They're just asking us to do the same thing again, but this time we're plugging in 4. So I think I'll need a calculator for that one. Negative 128 plus 20 is going to be negative 108. And once again, that tells us that at t equals 4, the velocity is negative 108. Use your answers from parts C and D to find the average acceleration on the interval from 2 to 4. All right, we can do that. So, average acceleration is t2 minus t1 on the bottom and v2 minus v1 on the top. So the two time values that we're looking at here are 2 and 4. The velocity at t equals 4, we found out from part D, is negative 108. And the first velocity at t equals 2, we found out from part C, is negative 44. And so if we simplify this expression, let's see what we'll get. Getting negative 32. And we want, oh, well, we don't have any units, so I can't put any units on there. But there would be the answer to part B. I'm sorry, part E. And now we have one more question to do, that's F. So let's take a look at F. So they want us to find S double prime of 3. So that means you're going to take your acceleration function and plug in 3. But as you can see, I can't plug 3 in because there's no t. So it doesn't matter what time value it is. It's always going to be the same. But what this does mean is it does mean that at t equals 3 seconds, like any other time, the acceleration is negative 32, and I was about ready to put feet per second, but we don't have units, so I keep forgetting about that. But t equals 3, the acceleration is negative 32. And what that means is that the velocity, you don't have to write this if you don't want to, but it's kind of helpful. The velocity is decreasing because it's negative by 32, and we don't know what it is, feet per second or what. So that would be that. So let's go ahead and have you guys try one like this. Go ahead and pause the video here and try out that number 2. When you unpause the video, you will see the solutions. Okay, so I'm going to show you the first 4, and then I'll show you the last 2 because I'm running out of space here. But part A, just find the derivative of the function they gave you, which is 3t squared minus 2, and that represents your instantaneous velocity because the derivative of a position function tells you the velocity of the object, instantaneous velocity. And if you find the second derivative, which would be 6t, which is the answer to B, that represents the instantaneous acceleration. For part C, they ask you to plug 1 into S prime, and into S double prime. And for those answers, I end up getting negative 1, 1, and 6. The first one tells you your position at t equals 1. The second answer tells you your velocity at t equals 1. And the last one tells you your acceleration at t equals 1. Part D is a repeat of part C. It's just that they do it with a value of 5. And so the first one represents a position, this one represents a velocity, this one represents an acceleration, all at the time value of t equals 5. So let's go ahead and move on to taking a look at parts E and F now. So basically on parts E and F, you're going to be using your answers from parts C and D. To find average acceleration on the interval from 1 to 5, you're going to use this formula here where you do your second velocity minus your first velocity over your second time minus your first time. Now the time they told us is 1 and 5, so that's what goes in the denominator. The velocity at 5 was 73 and the velocity at 1 was 1. And so v2 minus v1 over t2 minus t1 is going to be 18. So that would be your average acceleration, and that tells you how much your velocity is increasing or decreasing over time. In this case, it's positive, so it's increasing. Part F is asking us, it's actually a flashback question to yesterday's or last class's lesson. It's asking for average velocity. Whereas average acceleration is v2 minus v1 over t2 minus t1. Average velocity is s2 minus s1 over t2 minus t1. S is position. So you do your second position minus your first position and divide that by your t2 minus t1. Once again, our time values are 5 and 1. At t equals 5, my position is 115. And at t equals t equals 1, my position is negative 1. And so subtracting that, my position goes from 115 to negative 1. That's, actually goes from negative 1 to 115, which is an increase of 116 spaces over a time period of 4. 116 divided by 4 leaves me with 29. So that would be my average velocity, and the part E would represent my average acceleration. All right, and so there you guys have that. Let's go ahead and move on to our next topic here. Let's review some things. Now, when it comes to position, S, if you're on a vertical axis, whether you have a positive S or a negative S indicates something. A positive S indicates that you are above 0. A negative S represents that you are below 0. If you're on a horizontal axis, a positive S represents that you are to the right of 0. And a negative position represents that you are to the left of 0. Okay, so I want to remember that. We also applied this stuff to, oh, you know, I didn't include zeros. Let me back up a little bit here. Now, what if your position is 0? Well, that's kind of obvious. If S equals 0 on a vertical axis or on a horizontal, that basically just means you're at the origin. Okay? So if S equals 0, you're at the origin. You're right at the middle. You're on 0. Okay? Now let's go ahead and take a look at velocity now. When we're talking about velocity, a positive velocity, we said, means that you're moving up if you are on a vertical axis. And a negative velocity means you're moving down if you're on a vertical axis. If you're on a horizontal axis, a positive V means that you're moving to the right, and a negative velocity means you're moving left. So what would a 0 velocity indicate? Well, that means you're not moving up or down, nor are you moving right or left. It means you're not moving. The object has come to a standstill. It's not moving anymore. So that's how we would interpret the outcomes for velocity depending on the signs of it. And that's all review. But let's talk about acceleration. Now, acceleration is a little bit weird. So acceleration is something that causes an object to speed up or slow down. Okay? So I kind of like to think of it like this. Suppose you're out for a jog. Right? And you're just running at a constant speed in that direction. Well, let's say that you take your dog with you now. Gotta love these pictures, right? Let's say you're taking your dog out for the jog with you, and your dog all of a sudden sees a cat. Well, your dog is going to pull you, right? And if your dog goes faster than you, then basically what's going to happen is he's going to cause you to accelerate. So acceleration is kind of like pulling, if you will. Okay? So if you have a positive velocity on a vertical axis, I want you guys to think of that as the object being pulled upwards. And if you have a negative acceleration, that's pulling your object downwards. Okay? So it's kind of like a pull on the object. It's causing it to speed up or slow down, which is kind of like it's being pulled. On a horizontal axis, of course, then a positive acceleration means that you're being pulled to the right, kind of like our guy walking his dog there. And a negative acceleration would mean that you're being pulled to the left. And so if you have a zero acceleration, that means you're not being pulled. And if the object's not being pulled, that would mean that it has a constant velocity. So in other words, let's go back to our talk about the guy who's running his dog. Well, if he has a zero acceleration, that means he's not being pulled. The dog's not pulling him. So that would mean that the man's speed is not going to change. He's going to stay at that same velocity because he has no acceleration. Okay? So that brings us to a point where we're going to make some conclusions now. You can combine the velocity of an object with the acceleration of an object to determine whether it's slowing down or speeding up. Okay? A positive velocity, remember, that means we're moving either up or to the right, depending on what kind of an axis we're on. A negative velocity means that we're moving either down or left, correct? A positive acceleration means you're being pulled either up or right, and a negative acceleration means that you're being pulled either down or left. Now we could put these concepts together along with that story about a guy with his dog to kind of come up with an example. So if I have a positive velocity, that means my man is jogging. That's terrible. Oh well. He's jogging to the right. And if he has a positive acceleration, that means his dog is also pulling him to the right. So this guy's moving to the right and his dog's pulling him to the right. What's happening to this guy's speed? He would be speeding up, right? But let's say that our jogger was actually jogging left. But his dog sees a cat behind him and the dog starts to pull him that way. What's going to happen to the guy's speed at that point? If he's trying to go to the left, oh, you know what? I'm putting this picture in the wrong spot. I'm sorry. Let me back up a little bit. My bad. My bad. We want to have the guy have a positive velocity. Okay, so let's say he has a positive velocity. So that would mean that he's actually still going to the right. So he's still going to the right because he has a positive velocity. But since this is where we have a negative acceleration, his dog sees a cat behind him, and his dog starts pulling him to the left. So the guy's trying to jog to the right, but his dog's pulling him to the left. What's going to happen to his speed? Well, he's going to slow down because they're opposite from each other, right? What happens if the man has a negative velocity, which means that he is moving to the left now, but the dog has a positive acceleration, so the dog is pulling him to the right? What's going to happen? He's going to slow down again, right? Because they're opposites. Finally, let's say that our man has a negative velocity, so he's running to the left. And his dog pulls him to the left. Now what's going to happen to the man's speed? Now it's going to increase again, right? So here's our final conclusion then. The conclusion that we've reached here is that if A and V have the same sign, which means either they're both positive or both negative, then the object speeds up. If A and V have opposite signs, the object slows down. Okay? And so that is the relationship between acceleration and velocity. So if velocity and acceleration of a moving object have the same sign, then it's speeding up. If they have opposite signs, then it's slowing down. But what if the velocity is 0 and the acceleration is positive? What would happen? Well, think back to the story of the man with his dog. If his velocity is 0, what does that tell us about the man? That means he's not moving at all. If the acceleration is positive, that tells us about his dog. That means it's pulling him to the right. So what does that tell us? That would mean that the man is going to start moving to the right, right? If you're just sitting there at a park bench, for instance, and you're holding your dog's chain and he pulls you, that's going to tug you in the direction of your dog, right? Well, in the same way, this would be speeding up as well. And we could be specific. We could say to the right because the acceleration is positive. What if the acceleration is negative and you're sitting at the park bench again? Same thing. You're still going to be speeding up, but this time you're going to be to the left. Your object's pulling you the other way. Okay? What if your velocity is 0 and your acceleration is 0? That means you're chilling at the park bench and your dog's chilling. That means there is no movement happening. If your velocity is 0 and there's no acceleration, nothing happens. What if acceleration is 0? Notice I didn't tell you anything about the man. All this I'm using my analogy too much now. I didn't tell you anything about velocity in this. So if I didn't tell you anything about velocity, velocity for our story about the man and his dog is velocity represents the man. So if I didn't tell you anything about velocity, then I'm not telling you anything about the man. The man's neither moving. We don't know if he's moving left. We don't know if he's moving right. We don't know if he's just standing still. All we know is that there's no acceleration. The acceleration represents the dog. So that just means the dog is not pulling on him. And so in that case, if your dog's not pulling on you, then whatever your speed is, it's going to stay the same. So that would mean that you have a constant velocity if your acceleration is 0. Okay, so let's go ahead and take a look at a couple of problems here to kind of cement that into our minds. So for numbers 1 through 5, use the given information to determine 3 things. We want to know where the object's located. That's its coordinate. We want to know what direction it's moving, left, right, up, down, or not at all, and whether it's speeding up, slowing down, or constant. All right? So I'm going to do numbers 1 and 2, and I'm going to let you guys do 3 through 5. So first of all, on number 1, I want you to notice something that I put H-axis. That means we're dealing on a horizontal axis. So for number 1 on my horizontal axis, I am located at a coordinate of 2. That's what this is. This is my coordinate. I'm located at 2. You could say you're 2 spaces to the right because it's a positive 2. So let's do that. Let's be more specific. 2 to the right of 0. Okay, so there's my coordinates. My velocity is 3. Now, if I have a positive velocity, that means I'm moving to the right. And I have a positive acceleration here. That means I'm being pulled to the right. So now, if I'm moving right and I'm being pulled to the right, is this object slowing down, speeding up, or constant? Well, since the direction I'm moving in is the same as the direction I'm being pulled, that would be speeding up. Okay, let me take a look at the next one. The next one I put v-axis, so now we're talking about a vertical axis. My position is -3, so that means I am 3 spaces below 0. When we're on a vertical axis, it's either above or below. So in this case, it's 3 spaces below 0. My velocity is negative. On a vertical axis, that means you're moving downwards. Now, I have a positive acceleration, which means I'm being pulled up. So if I'm moving downwards, but I'm being pulled up, those are opposites. So I'm going to end up slowing down. Okay? Go ahead and pause the video here and see how you guys do with 3 through 5. And then when you unpause the video, you'll see the answers to that. And then I think we'll also have you guys go ahead and just do all of these problems here. Let me lower my screen a little bit so you guys can see the rest of number 10. And have you guys go ahead and do all of these, 3 through 10, and when you unpause the video, you'll see all the solutions. All right, so for 3 through 5, I'll let you study those. Those are pretty straightforward. Numbers 6 through 9, we'll talk about. Number 10, I don't think that's answerable. I think my question's bad, so we'll ignore that, and I'll explain what I was trying to go for with it, but I don't think it's worded correctly. But let's go ahead and take a look at number 6 here. Which object went the highest? So when we're talking about height, that has to do with a vertical axis, so it either has to be object 2 or 4. Now, for object 2, its position was -3, and after that it went down. For object 4, its position was 4 and it went up. So object 4 is the one that would be reaching the highest height. Okay. Which object was farthest to the left? So if we're talking about going left, then that's going to pertain to a horizontal axis. So we're going to look at these 3. Now, first of all, let's see which one of these was furthest left. We have 2, -3, and -10. So number 5 would be the one that was farthest to the left. Next, we have number 2. Which object was going the fastest? So for that, we just want to look at velocity. So, but you take the absolute value of it because fast is speed. So which one of these has the greatest absolute valued velocity? And the answer to that would be number 2. Number 2 has the fastest velocity. The absolute value of -4 is 4, and that's bigger than any of the other absolute values there. So the answer to that one would be number 2. Which object was slowing down the most? Now, slowing down is whenever the acceleration and the velocity are opposite signs. So we had that here, we had that here, and that is it. Okay, so those are the 2 situations where my velocity is slowing down, or the object is slowing down. So which one's slowing down the most? Well, the one that would be slowing down the most is the one whose acceleration is greatest. The greater your acceleration, the more quickly your speed is changing. So the answer to this one would be number 2. Now for number 10, like I said, I think it was just badly worded. I think I meant to put if the object in number 5 has a negative acceleration, which is what it does have. If it has a negative acceleration, where was this object just before it reached s equals -10? Well, the answer to that would have to be above. So we have this object that's moving upwards, but the problem is it's being pulled down. And since it's being pulled down, its speed is decreasing, although it does keep trying to go up. But pretty soon, the acceleration becomes so great that it just stops moving. And then after that, the acceleration starts to pull it downwards. Okay, so if the object has a 0 speed at this point, where was it just before it reached that point? Well, if it was slowing down, then it would have to have been to the right, because after that it's going to start pulling it to the left, right? Oh, and actually I just realized I put pulling down here, but this is supposed to be speed. This is supposed to be left. So, but that's kind of a confusing one. I wouldn't worry about it. I think it was badly worded. So example 2. These are called rectilinear motion problems. It's actually not a word you really even need to know. I don't know why I put it there. Maybe it just makes me feel smart. I don't know. You don't need to know that word. It's okay. But basically, anytime you're dealing, this is actually a really common type of question, though, even though you don't even know the name of it, is dealing with questions where they're talking about particles moving along an axis. Really common. You're going to see one FRQ question on your AP exam that deals with particles moving along an axis. So it's a great introduction to it. So here we go. An object is traveling along the x-axis according to the position function given below. Answer the question that follows. Now, since we're traveling along the x-axis, I'm going to go ahead and change it from s to x, just because that way it makes a little bit more sense. T represents time. So basically, I could plug in a t here for time, and it will tell me the x value. In other words, what point I'm at on the x-axis. Okay? So let's go ahead and get started here. So there's my function that tells me the position of the object at any given time. And the position is measured in centimeters and time is measured in seconds. They want me to find the position, the velocity, and the acceleration when t equals 2. All right? So to find the position, basically we're just going to be plugging the, I don't like how that's highlighted. There we go. We're just going to be plugging the time value of 2 into the original function. So 8 minus 16 is negative 8. And so what this tells me is that this object, which is moving along the x-axis, will be at a position negative 8, which means it'll be 8 spaces to the left of 0 at time t equals 2. Now, if you wanted to find the velocity, in other words, how fast and in what direction is that object moving at t equals 2, we're going to need to find the derivative of x with respect to t. So x prime would be 3t cubed minus 8. Okay. Now, we don't usually see x prime, right? We're used to seeing y prime, and that's because usually y is our output variable. But in this case, it's x is my output variable, so we're finding x prime. By the way, another way to write this instead of x prime would be we're finding how fast x is changing as time is changing. So dx dt would be another way of writing that. But we don't need to get into all that fancy stuff right now. We just need to make sure we know the derivative. So the derivative is 3 times t squared minus 8. And in this case, we're finding out what is the velocity when when t equals 2. So we plug 2 into the velocity function. So that's going to be 4 times 3 is 12 minus 8 is 4. So this is, I forgot to put my units as well. For the first one, this would be negative 8 centimeters. And for this one, it's going to be 4 centimeters per second. Okay? X is measured in centimeters, t is measured in seconds. And so velocity is centimeters per second. Finally, they want us to find the acceleration. So if you want to find acceleration, then you're going to find the second derivative. So x double prime would be the derivative of this thing over here. And this was supposed to be a 2. I wrote that wrong. All right, so the derivative of 3t squared minus 8 is 6t. So 6 times t, and we're plugging in 2 for t. And so my acceleration would be 12, and the units for acceleration are distance over time squared. So centimeters per second squared. Right? Now, the last question they want me to answer after they find position, velocity, accelerations, they want to know, is the object speeding up or slowing down? Well, my velocity is 4, so my object is moving to the right, and my acceleration is 12, which means it's being pulled to the right, and since it's moving to the right and being pulled to the right, we would say that it is therefore speeding up. So let's go ahead and throw one of these things your way. Go ahead and pause the video here and you try one. All right, and so the position at t equals 2 would be 4 meters. The velocity at t equals 2 would be negative 10 meters per second, and the acceleration would just be negative 10 meters per second squared. Since both the velocity and acceleration have the same sign, they're both negative, it would be speeding up. All right, let's move on to our next question. A pebble is dropped into a pond, causing ripples in the form of concentric circles, and the area of the circle is given by this function. So basically with this function here, if you plug in 1, it will tell you what the area of the circle is after 1 second in square feet. And if you plug in 2, it'll tell you the area of the square after 2 seconds in square feet. So let's go ahead and work this stuff out. So they want us to find a of 2, a prime of 2, and a double prime of 2. So here's a. That means that a prime, or in other words, dA dt, if you want to write it like this, derivative of a with respect to t, that would be 8 pi t. And then a double prime, or if you want to write it in this notation, you write it like that, second derivative. A double prime is just the constant that's in front of the t now, because the t just goes away when you find the second derivative there, and so it's just 8 pi. All right, so there's our derivatives. So let's go ahead and plug in our 2 then to this. So still answering number 1. A of 2 is 4 times pi times 2 squared, and that's 16 pi. And that's going to be in square feet. And the way you write that is just feet squared like that. Okay, so that's the answer to A. Anytime you're measuring area, area is in square feet, just so you know. All right, well, not number 2. We're still on number 1. But now we want to find a prime of 2. And a prime of 2 is going to be 8 times pi times t, because that's the velocity function there, if you will. And that's also going to be 16 pi. But the units are different. The output units are square feet, so feet squared, and the time unit has to be included down in the denominator per second. And so this one tells you basically what the area is at 2 seconds. So at t equals 2, the area of the circle is 16 pi square feet. This one tells you how fast the area is changing. So at t equals 2 seconds, the area is increasing at a rate of 16 square feet per second. Okay, now I'm not going to write these interpretations out just because I'm kind of low on space here, as you can see. As for the last one, a double prime, if you plug in 2, you can't plug 2 in, there's no t. So the answer is just 8 pi, and that is going to be in square feet per second squared. Okay, remember velocity is going to be the output unit, which is square feet, over the time unit squared. So it's square feet per second squared. And what that means is that at t equals 2, the rate at which the area is increasing is itself increasing by 8 pi square feet per second. So the area of the circle is increasing by 8 pi square feet per second every second. So there's that. Is the rate at which the area increasing, speeding up, or slowing down are constant? Well, both the second derivative and the first derivative at that point were positive, right? Since they're both positive, we would be speeding up. So the area is increasing at a faster and faster rate, is what that would indicate. All right, and here's one for you guys. So go ahead and complete the exercises on this page, and then we'll be done for the day. So it looks like I didn't include units on this one, so we'll ignore the units this time around. But the position of the car is 99 spaces or 99 units to the right. The velocity is 33, which means that it's increasing its position by 33 spaces to the right every unit of time that goes by. And then the acceleration is negative 16.5, which means that it's actually slowing down. There's a force acting on it that's pulling it to the left, so to speak. Which, when you're thinking about cars, you could think of that as like putting a brake on, right? And so since the velocity and acceleration are opposite signs, this vehicle is in a process of slowing down. But that's pretty much it for the day. So till next time, we'll see you guys then.